so this lecture will talk about frequency response or frequency domain analysis, and you see the similarities with the Z transform. So the outline of the lecture will talk about the introduction of discrete time Fourier transform DTFT and some properties about it and their pairs. Actually, like we apply the formulas at the beginning, but you realize later there are pairs. So basically, delta will lead to 1. The sign or e to the power j something will lead to something omega naught, omega minus omega naught, things like that. So those are the properties. All right. So introduction to DTFT. The formula, if you look at it, so x of e to the power j omega equals summation from negative infinity to infinity, x of n e to the power minus j omega n. Now remove this hat just to keep it omega, that's 1. Now if you compare it to the Z transform, f of z, it used to equal from n equal to negative infinity to infinity, f of n z to the power minus n, right? Or there is difference? Yeah, we said f of n, or let's just stay consistent. Let's say this is x of z, and this is x of n. Now, when we substitute z equal e to the power j omega, then we'll get that expression. So you'll get then e to the power j omega to the power minus n. Since this one is raised to that power, they will be multiplied e to the power minus j omega n, and that's exactly the same expression I'm getting here. So we can use our knowledge in the Z transform and apply it into the DTFT. So that's what we call forward transform. Basically, you're going from the time domain into frequency domain. Going backward from frequency domain to time domain, we call it the backward transform or the inverse transform. So if h of n is the impulse response of a linear time invariant system, then the DTFT of h of n is the frequency response h of omega. Exactly what we have done on the Z transform. So impulse response, take the Fourier transform for that, or the Z transform, whatever, you will get the frequency response. Good note here that the DTFT is always periodic over 2 pi. And this one could be easily proved. So e to the power minus j. And since we say periodic over 2 pi, you can say omega plus 2 pi n. So we'll check how much this one equals. So let's distribute e to the power minus j omega n minus e to the power, times e to the power minus j 2 pi n multiplied. Now this one we can apply the Euler identity, so it's going to be cosine 2 pi n minus j sine 2 pi n. Keep in mind that n is always integer. And what does that mean? So here I'm taking the cosine of multiples of 2 pi. So if we have the coordinate system like here, 2 pi, that's a whole circle. So it's like 0. 4 pi, another circle. 6 pi, another circle. So it always go back to this one. So when you take the cosine of 0, so that's going to be 1. Okay, who's joining? Please, okay, Janahi. There you go. All right. So we'll go back here to the lecture. So yes, when we have n as an integer, so we'll have the angle technically 0. Now the signs here, that's going to be always 0 because sine of 0. So you multiply e to the power minus j omega n times 1. And that's what we mean by periodic. So let's assume in the final exam, you may face a question like this. Prove that DTFT is periodic over 2 pi. And this is the proof. So basically you start with omega plus 2 pi times n. So that means that after 2 pi is going to be the same function. So basically you start like this. E to the power minus j j omega n. Does it equal e to the power minus j omega plus 2 pi n? So that's how you start solving this question. Then you work on this expression using those values here, and you will get that they are both equal. So that's the proof. Okay, so let's move on. Now, when you have a shifted version of a function, let's say, for example, this one as the impulse. So when you take a shifted version of the impulse, if you remember any function multiplied by the impulse, n minus n naught times x of n, you will get x of n naught. Discrete x of n naught. So we'll apply the same thing here. Then the summation will be from n equal negative infinity to infinity. Now apply what we have done there. You will get e to the power minus j omega n naught. And since the summation over n, and there are no n's here, it's going to be the same value, e to the power minus j omega n naught. And also this one means that this summation for all points of n, it has only value at n naught. All others will be 0. So let's give it some value here, and all others will be 0. So the summation also will be meaningless because all other values will be 0 and it has only one value at n naught. This could be generalized for any function. It doesn't have to be delta. So let's assume it this way. If x of n will give me x of e j omega, then x of n naught will give me x of e j omega, same, times e to the power minus j omega n naught. So n minus n naught. x of n.
دكتور لو معلك أمر ممكن الليكتشر هذا في مودل؟
You want it now?
إيه لو ممكن.
All right, sure.
شكرا.
Okay, let's discard the annotations and open model. So today is second here. Okay. Let me save it. Okay, and F50 together. Taking forever. I'll put them here and move them. I think. Okay. So that's lecture 9, lecture 8. Did I put the eight? All right, can you see it now? Check.
Hey, شكرا.
All right, no worries. Lecture 8 from current slide. All right, we'll go back to the properties later, but this one for delta, because we know delta of n, the z transform will be 1. And again, z transform and the DTFT, they are kind of similar. Instead, you just change z to be e to the power j omega, and they are all set. So that's why I don't see this chapter challenging, because it's kind of repetition to the z transform. But now we are dealing with omega instead of the frequency values. Linearity also applies here. So if you multiply a constant with a function, then you multiply the constant with the transformation. Addition, you apply the addition for both sides. All right, so here an example. Find the DTFT of the impulse and of the impulse response of the following FIR filter. So basically, they want h of j omega. Why? Because find the DTFT of the impulse response. Impulse response h of n. DTFT h of ej omega. Now simple, we know that h of ej omega equal y of ej omega over x of j omega. Now let's do DTFT here. So y of n will become y of e j omega equal 3 x. Now x immediately j omega. Now I'm having a shift by 1 e to the power minus j omega 1 plus minus. So this one here, that's the answer for it. Now this one, 2 lines. So I have 2. I have x, so it's going to be x of e j omega, then multiply by minus j omega and negative 3. So it's going to be 3. So that's the other part. Third part, I'll do it with a curly line. So plus 3x e j omega e to the power minus j omega 5. Double check. Yeah, just that you multiply by the constant. Now, like what we did in the z transform, we'll take x of j omega as a common factor. So y of e j omega equal x of e j omega common factor, and I will have those together. 3 e to the power minus j omega minus 2 e to the power minus j omega 3 or 3j omega, whatever you want to write it, plus 3 e to the power minus j omega 5. And then you just divide over x, divide over x. So this is the final answer. Is it clear by so far? Anything complicated? All right, so all is good, inshallah. All right, let's continue. Now, when you have a step sequence, what do you mean by a step sequence? So you have a unit step function weighted by a certain coefficient or coefficients multiplied by the, multiplied by the set of coefficients. So pretty much like this one. So the DTFT for this one is like, assume you have a to the power n, 2 of n. So this coefficient here will go back to the denominator. So you will have 1 here, 1 minus, and that's a. That's the a here, but without the n. E to the power minus j omega. Again, related to the transform, exactly the same shape. A is to the power negative 1. So similar to the transform, whatever we applied there will be applied here. Now, y absolute value of a should be less than 1 for stability. Because here you want to have the poles inside the unit circle in case we are dealing with the z transform. All right, let's see where else. Finite condition, pretty much similar condition. So for the function to be, let's see, to have existence in the DTFT, it must be absolutely summable. It means that summing all coefficients will not lead to infinity. So it should be always bounded, should be always less than infinity. Now, inverse DTFT, similar expression. However, here we divide over 2 pi, and the integration is going to be from negative pi to pi. Good thing here that we rarely rely on the actual formula. Once we go into the pairs, will be, let's say, just a comparison or easy. But doing the formula is not complicated. Sometimes you might need to do integration by parts or by substitution, but questions usually are not complicated. We'll check the worksheet right now, and if you guys seen in previous assessments, questions are not very far from the worksheets. Okay, some properties. So here we've done that. So shifting, or sorry, periodic or periodicity. So if you add 2 pi at the exponent, it will lead to the same function. Linearity, we've done that. Time shifting, if you shift in the time domain, you multiply by an exponent in the frequency domain. Frequency shifting, it's the opposite. And so when you shift in frequency, you will get a weight in the time domain. Yeah, this one you don't deal with it pretty much like this one. This one is the common one. So here is an example here, y of n, you multiply by a certain constant. It means that the Fourier transform will be shifted. So here, let's assume this is the Fourier transform of x of n, the DTFT of x of n. When you multiply it by this one, you shift by pi. And it's noticed here that this one, the peak was at 0. It moved to pi. So it's shifting to the right by 2 pi. Again, it's not a very complicated thing. You just need, like most likely in the exam, I will ask you direct questions. Huge table for the properties. You don't have to worry about it. That's the table you will face in the exam. And so you have delta of n. You have delta of n minus nd, so that's a shift. So this one is a rectangle, if you guys remember, u of n minus u of n minus l. So basically, it's a rectangle with a length of n. So 0 to n, to l, sorry. Now this one in continuous domain, the actual one will be, should be something like this, like discrete points. So l points. So in this case, the Fourier transform or the DTFT will be this expression immediately. So you just know the value of L. Here, R of L weighted by e to the power j omega naught n. So this one you have this expression, you multiply it by omega naught n. Remember, multiplication in time domain will lead to a frequency shift in the frequency domain. So here, for each omega is going to be omega minus omega naught, omega minus omega naught, omega, omega minus omega naught. So all of omegas will be omega minus omega naught. Here, that's what we call a sinc function. So sine omega n over pi n. The representation will be 1 for absolute values of omega less than omega b. So basically something like this. So that's omega b, negative omega b, and that's the representation. You have a 0. Again, it's a rectangle. So that's what we call a duality principle. A sinc will lead to a rectangle, and a rectangle will lead to a sinc. For the unit step function to be with a condition of a less than 1, that's the transform we have seen a while ago. I'll just this one here because it's way below. Let me see if I can put it in a better location. So this one here is similar to that one. So like notice these two functions. So a and b. So like if you assume A and B are equal, both questions are identical. However, if you look at the question here and the question there, or the formula here and formula there, they are totally different. So this one shows that the DTFT is not unique. So you might have two functions having the same Fourier transform or DTFT. Some usages of DTFT is development of filters. We already know that this is a low pass filter. That's a high pass filter. Band pass filters like that. You don't have to worry about the expressions, but you should know that when the frequency is low. So this one, if I want to give it a representation, H of EJ omega equal 1 for absolute value of omega less than omega C naught, which is this one given here, and 0 elsewhere. This one is the opposite. H of EJ omega. So this one usually call it LPF, low pass filter. So this one is HPF, high pass filter, equal. It will be like this 1 or absolute value of omega larger than omega C naught and 0 elsewhere. Okay. And this is the representation for a high pass filter. So you have zeros. It has two cutoff frequencies, C1 or C1 and C2. So if it's below C1, so it must have a 0 value. Between C1 and C2, it will have a high response, and C2 to pi will be 0. Again, it's periodic from negative pi to pi. Now, from this slide, I want you to memorize or understand what is a low pass filter, what is a high pass filter, and what is a band pass filter and band stop. They don't have band stop here. Like just a representation in the exam, I may give you this figure. I'll tell you what filter is this. Similar thing here, like this one from the shape. You should know that's a low pass, that's a high pass. All right, filtering design. So in order to make a practical design for filter, we can multiply the sinc function by a window to produce L impulse response. So there is a process called windowing. I'm not going to go into details here. Basically, it says that you cannot have an ideal filter like that. It's impossible. So what you do is you have something close to the filter, close to that rectangle, because here is very sharp and you need an infinite order filter to make that. So, and that's not causal. So you will have an issue there. It's not practical to have a filter like that. So you always have something like this. Like it's not sharp. There's a rise time and there is a slope time. And also the gain here cannot be perfectly one. It must have something like this. We call it ripple. Same thing here. There are stop band ripples. All right. So example of windowing. That's a Hamming window example, and that's it. So again, this topic is easy, not complicated. So let's start working on the worksheet on this one. Okay, tutorials. Let me do it with the solution because we may not need to do a solution or detailed solution. So for example, that's pretty straightforward. We have 2 times delta n negative minus 4. So that's going to be 2 times e to the power minus 4j omega and 4j minus omega 7. Similar thing here. You have a unit step function. So 2 minus 2. Okay, in fact, this one could be expanded. This one here, I will not say it's a tricky function, so let me solve it actually. Okay, let me see, it's 2, 2, 7. So you have x of n equal to u of n minus 2 minus 2 u of n minus 7. Now I close the slides, okay, with the tables there. Yeah, so we have this shape here. Like, keep in mind, like when you have two unit steps and there's a minus sign between them, I'm creating a rectangle. So I need to apply this expression. That's one hint. The other hint, we did not do a u of n example. Even though we know u of n will give me 1 over 1 minus e to the power minus j omega. So when you have u of n minus 2, you say it's going to be e to the power minus j omega 2 over 1 e to the power minus j omega. Could be fine, but that's not the solution that I'm seeking. All right, so keep in mind, we have a rectangle, sorry, a unit step minus a unit step, I'm making a rectangle. So if I want to draw this expression, I have 2, that's 2, 3, 4, 5, 6, 7. Okay. And all of them of magnitude 2. So what is the length for this filter? It's simply 7 minus 2 equals 5. Even though someone might ask, okay, we have 6 points, but no, I'm looking at the difference. 7 minus 2. So the length for this one is 5. All right, so that's one piece of information. That's 5. Now, what if the function was like this? 2 u of n minus 2 u of n minus 5. If I want to draw this one, I will get like this. At 0, 1, 2, 3, 4, 5. And each one of magnitude 2. What is the similarity between those? Any similarity? They are similar in shape. However, I'm starting from 2. Here I'm starting from 0. So this one is shifted by 2. Now my function, see how this problem is approached. My function, let's assume, let's call it x of n equal to u of n minus 2 u of n minus 5. That's my question. Now I want to find x of n minus 2. That's going to be equal to u of n minus 2 minus 2 u of n minus 7. You see how to approach this problem? So make sure that you know how much the amount is shift, that's L. Sorry, how much is the length of the rectangle and how much shift from the original expression, because in the exam, you are given this expression. But I'm doing some shifting. So first, let's find this one. And it's pretty easy. I have L equal 5, so I'm gonna copy this one as it is. Okay, like this. Copy it. And here is the solution. That's for u of n minus u of n minus 5. And instead of L, I will put 5. Now, when you say I have to take it as a common factor and multiply this whole expression by 2. This is a 5 here. So let me rewrite it. I will have 2 sine 5 over 2 omega over sine 1 over 2 omega e to the power minus j omega. Now 5 minus 2, that is 4 over 2, that is 2. Is it clear so far? Any questions?
Doctor, can you repeat it again?
All right. From where? Like, do you have any specific point or repeat the whole thing? I'm not done, by the way. This question is not done yet because this is x of n. Now I have x of n minus 2, which is u of n minus 2 minus 2 u of n minus 7. That's the question. So e to the power minus j omega 2. Why? This is came from the shift 2. And those could be easily added e to the power minus j omega 4. So both of them. Okay, I will repeat it. So just a key point here, when you have u of n minus 2 minus u of n minus 7, I have 2 here, 2 here. The moment you see 2 unit steps, the formula, this expression should be there. This one. Or let me copy the whole thing, go back here. So when you see two step functions together, probably my question is regarding those. However, this one is not in the standard form like this one. I have u of n minus u of n minus l. Here I have u of n minus 2 u of n minus 7. So I have a shifted version of this. Now, what is the original version? That's it. You look here, there's a value 2. So I want to subtract 2 from both sides or remove 2 from both sides. So basically, this one will become 2 u of n minus 2 u of n minus 5. Then I'll add a comment shifted by 2. But this is my original now. This is my original function. But it was shifted by 2 that gave me this expression. Now I know when I do shifting in time domain, I'll do scaling multiplied by an exponent in the frequency domain. So let's find the frequency domain first. This one here is similar to this one, but I can find that L equals 5. So in this case, in my example, L equals 5. So just immediately, I'll just copy this expression as it is and substitute L equals 5. And do not forget, there's a constant 2, there's another constant 2. So take it as a common factor, u of n minus u of n minus 5. Now this will lead to 2, it's a constant, multiply by the same exact expression with the value of L equal 5. So you will get sine 5 over 2 plus 1 over 2 times 5 omega over sine 1 over 2 times e to the power minus j omega. Now L minus 1 times 2. 5 minus 1, that's 4. Sorry, divides 2. 5 minus 1, 4. Divides 2, that's 2. Okay, so I found the DTFT for this. Now apply shift by 2. So shifted by 2 will lead to multiply by negative j omega 2. So whatever expression here, sine, rewrite the whole thing again, sine 1 over 2 omega e to the power minus j omega 2 times this one here. So this one is from the shifting. Time shift. And you can basically combine them. So the final answer will be 2 sine 5 over 2 omega over sine 1 over 2 omega e to the power minus j omega. And that's it. That's the final answer. Let's confirm. All right. So e to the power minus j2 omega sine, and I have j omega 4 over 2, which is 2 omega. We can combine them. I will get that answer. Is it clear? Any questions?
Doctor, can we solve another one? Another questions? And like
Same concept.
part C, hey. Or part
Part
A.
C, C is deltas.
Okay.
Okay, I'll give you this question and try to practice it. X of n, 3 u of n minus 7 minus, so this one is 3, this one has to be 3, otherwise it will get a little bit messy. Could be solved. I'm not saying it's not going to be solved. Could be so. It will be solved, but I don't want to make things harder. N minus 10. So looking at this one, start by doing this. How much is the shifting? Shift by how much? Shift. So this is the value of the shift. That is 7. What is L? The length is 10 minus 7 equal 3. The length is this one minus this one. It's the length of the rectangle. So that's it. Now, actually, to make it extremely simpler, once I have those, I don't want to do the standard classical approach, whatever. This will immediately become like this. I have the 3 sine. What's the value of L? 3 over 2 omega over.
دكتور ليش ما قلنا من الشفت 10؟
لا. Shift how much?
10.
لا, مو عندنا rectangle. We have the rectangle like this. So that's 0 to 3. Now shifted by 7. I will get the rectangle like this. From 7 to 10. So I'm shifting by 7 because I'm starting from 0. All right, sine 1 over 2 omega e to the power minus j omega L minus 1 over 2. 3 minus 1, 2 over 2, that's omega. Times, so this whole part because of L, e to the power minus j omega 7, that's from the shift. And that's it. 3 sine 3 over 2 omega over sine 1 over 2 omega 8. Get it? More or less?
It's good. بس دكتور بس ثواني قبل تشيل هذا.
Alright. Most important part here is to determine the values of the shift and the length of the rectangle. Once you get those, it's just direct substitution to the formula with the length, and then you apply the shift.
دكتور ممكن ترد لي السؤال اللي قبله؟
Okay, all is good so far?
Yes.
So we can continue with the examples. So this one sine 0.6 pi n over 5 pi n directly from the table here. So omega b is 0.6 pi. And that's the answer here. Convert the following signals into discrete domain using IDTFT. So going backwards now. So I have a constant for j sine 5, 3 cosine, etc. Now someone might ask, okay, what is 2 pi? It's a constant, so there is a delta involved. Okay, so keep in mind. And by the way, we are not going to be using the formula. Most of the time we'll be looking at the tables. So we have a constant, there are no omegas, so there is a delta. However, the delta is multiplied by 2 pi. So here, what is the function that gives me 2 pi in time domain is 2 pi delta n. Now we have 4j sine 3 omega. Now how to get this one? Remember from Euler identity, 3j sine 3 omega. Okay. Y of e power j omega equal 3j sine 3 omega 3 omega. Okay. So if you look at the table, now we are going backwards from the frequency domain to time domain. So we'll go to the table and check the frequency expressions. None of them has a pure frequency, a pure sinusoidal, a pure sine or cosine. However, we know from Euler identity, and okay, we know that e to the power minus j sine, j omega equal cosine. Let me use alpha to avoid confusion with omega. Cosine alpha minus j sine alpha. And we know e to the power j alpha equal cosine alpha plus j sine alpha. Now, why I'm doing this? If we subtract each one of them, do subtraction, the cosine and cosine will cancel each other. So here, let me try cancel, do the subtraction this way. So this expression minus this expression. So I will have e to the power j alpha minus e to the power minus j alpha equals j sine alpha minus j sine alpha to j sine alpha. All right, is it clear what I've done? So I started with the standard Euler identity. E to the power plus minus j alpha equal cosine plus minus j sine alpha. Now I am doing this, I want to switch from the sinusoidal form to the exponent form that I can see. All right, so divide both terms over 2j or 2. Let me divide over 2j. So I will get the sine alpha equal e to the power j alpha minus e to the power minus j alpha over 2j. Now this expression, I can make it related to this one. Now my alpha is 3 omega. So sine 3 omega equal e to the power j 3 omega minus e to the power j negative 3 omega over 2j. Now I can substitute this instead of this. So y of ej omega 3j times e to the power j 3 omega minus e to the power minus j 3 omega over 2j. J and j will cancel. 3 over 2 e to the power j 3 omega minus 3 over 2 j 3 omega. I just did subtraction and substituted, distributed 3 over 2 over these two terms. And for each one of them, I can easily find it. So I have shifted versions of delta. So it's going to be 3 over 2 delta of n minus 3 minus 3 over 2. Okay, this one is plus 3 delta of n minus 3. Because delta of n minus n naught. Okay, delta. Okay, let's not forget the basics. Minus j equal minus j n naught. And that should be the answer. We can confirm here. 2 and 2. I think there is the 3. That's 4j. Okay, 4j. I copied the 3. So, okay. Instead of 3, that is 4. That is 4. 4. 4. This is a 4. So 2 delta n plus 3 and 2 delta n minus 3. So that's second question. Is it clear how I did it? By the way, I might be a little bit fast, but this is a recorded session, so I'll give you the recording so you can work on it later on. But start with the Euler identity. Do this, let's say, it's like of eliminating a variable. So I eliminated the cosines. So I'm left with the sine and exponentials. Exponentials are easier to deal with when you work with the Fourier transform. So this one, there's the sine. I want to get rid of it. I did the simplification, I removed the sine. I went back to the exponentials and it was easy to be fine. Similar thing could be applied with the cosine question. So try the cosine question and the final answer is there. Alrighty, and that's it for this lecture. Stop sharing. Or any questions before we move on to the next lecture? Do you have any questions? Okay, no questions. So we'll stop the recording for this one. Okay, more record. Stop recording. Stop.